SwayamPrabha. Digital India. Educated India.
So we are on lecture 4 of the machine learning answer. Can everybody mute themselves, please? So machine learning for inverse heat transfer series. So we'll be looking at gradient descent today. So recall that we had this model which we discussed yesterday, the neural network model. Very simple idea. In a linear model, we start with the input, just take a linear combination of that and we get the output. In a neural network, all you need to do is, apart from that linear combination, you run it through a non-linear operation. Okay, so this essentially is the forward data model. Okay, so it's a good idea to see it as that. What I mean by a forward data model is that just like we had functions which we wrote, we'll just assume that a neural network can approximate whatever function we want reasonably well. You will see how to use this in the next week. But within the neural network itself, so like I said, globally we want to solve an inverse problem, such as finding out conductivity. But within that, you have to solve another inverse problem if you are using neural networks. And the inverse problem is find out these weights. Okay, so let's call these weights W1, W2, etc. So we have 50, 60 weights, actually far more than that, in this particular neural network that I have shown. Okay. Now, what we are showing here is a graphical representation. It is always useful to remember that there is a corresponding analytical form to that graphical representation. 1 minute. Yeah, so every graphical representation has a corresponding analytical form and vice versa. So my question is this, let's start with this simple question just to start off. How would you represent a quadratic model? Can somebody give me the answer? What I mean is, see, this is the graphical representation of a linear model. What would be the graphical representation of a quadratic model? Anyone?
Weight itself is x1, sir. Xi.
No, weight is not xi. W0, W1 are the weights. Thanks for pointing.
Put another weight W2 and then x square. So W0, x0
Okay,
plus W1,
so
x1.
suppose quadratic is, sorry, somebody said something.
Yes, sir. W0, x0 plus W1, x1 plus W2, x square.
W0 plus W1x plus
W2, x square.
Perfect. But how do I draw it graphically then?
Double lines.
Double lines meaning? So how will I change this particular graphical representation I have here?
I had another input.
We have one input only, x, but it branches into two parts, x and x square. And then from x, one weight of W1 goes, and from x square, one weight of W2 goes to the signal.
Okay, that is one possibility. But let me point out that the simplest way to do it, in some sense, and you would have seen this earlier in the course, is to treat it like this. Now, this is not intuitive for most of us. So W0, W1, W2. Okay, so now if you see, the actual independent things that we are entering are simply 1 and x. So these are called the attributes. Attributes is the raw independent information that we are sending. Okay. These, which is 1, x, x square, are called the features. So in some sense, you can say we have two attributes, or you can say you have one attribute, because one, really speaking, is not an attribute, but you have two features. Okay. So this, whatever goes in the input layer, is a bunch of features. For a quadratic model, you have two features. For a cubic model, you have three features, so on and so forth. And what is the advantage of writing it this way? Now, this still looks like a linear combination of the features. So what might be a non-linear combination of the attributes will actually be a linear combination of the features, in case you are looking at a linear model. For a neural network, we still have these features. Now, for example, these features could be one variable x1, another variable x2, another variable x3, and a fourth variable which I can call x4, but x4 could actually be x1 times x2. Okay. Which way you represent this depends on your cleverness. Okay. So for example, if we have a quadratic model, so let's say we have data that looks like this, it's growing quadratically. What you can say is the model is W0 plus W1 x1 plus W2 x2, or you can even say W0 x0, where x0 is 1, x1 is x, x2 is x square. Okay. Now all the models that we are looking so far will simply treat mathematically some set of linear combinations which are x0, x1, x2. Now x0, x1, x2 themselves could be functions of your attributes in some way or the other. Okay. So let me now go back to a very old example. Okay, so the old example, I think this was the very first example that you did in this class. We were looking at steady state heat conduction in the slab, and we had collected data from 5-6 points. So let's say 6 points we have collected. The question was estimate the correlation coefficient, also estimate the flux. Okay, first estimate the flux and then estimate the correlation coefficient. Okay, all of you remember what we did. We actually knew that the model is this. Okay, but because of that, we actually use a least square linear regression model. Okay, and the linear regression model, in my terminology, W1 is A and W0 is B, and you solve for it directly. And how do you solve for it? You basically write, one second, this total S as yi. Remember, yi is the actual data, which we will call ground truth, minus y hat I, and y hat I is my linear model, correct, this square. And we said find W0, W1, or A comma B, which minimizes S, correct? So this is what we had done. How do I write y hat I in terms of W0 and W1? What is the model?
It's a
Sorry?
W0 plus
find Z and take Z of that.
W1 xi. Do you agree? If I am looking at the third point, the prediction, what we call y fit here, that's what I am calling y hat. Okay, this is just so that I am switching from one notation to the other, because this is the general notation you will see in I can easily use Professor Balaji's notation, but that's not what you will see in machine learning textbooks. So I'm just trying to gently transition you to that kind of notation. Also, instead of S, you will see J. J is simply the function that we are minimizing. Okay. So what we did, how did we find out this expression? Where did this expression arrive from for A and B?
By differentiating S and with respect to the parameters and equating it to 0.
Okay, very good. So what we did was we differentiated del J del W0 equal to 0, del J del W1 equal to 0. We solved that and we obtained these relationships. Correct? Okay. Now let us say I had this lab. I am going to suggest two problems and this will tell you why it is that we are going to move to gradient descent. Okay. So this method works very well. Why start some other algorithm to find out? So basically gradient descent is an algorithm, an alternate algorithm to find out W0 and W1. But we are already analytically able to solve it. Now let us say there is this problem and instead of this, I had a heat source. Okay, and the heat source is a constant. Let's call it QV. That's if you have done heat transfer, we typically call it QV. Okay, so for example, in this equation, instead of saying d square t dx square equal to 0, I would have k d square t dx square equal to minus QV or plus QV depending on whether it's a sink or a source. Okay. Now, what would be the solution to this problem now? Would it be linear? What will it be?
Quadratic.
It will be now a quadratic. Okay. So did all of you do a quadratic regression also in this course? Finding out an expression for A. So now instead of having A and B, you are going to have A and B and C, or in my terminology, W0, W1 and W2. Is that correct? How are we going to get these three now?
Same procedure, sir. Go
Same
by
procedure.
W0 equals 0 and we get three linear equations. We
You will
put
get
them
three
in
linear
different.
equations and you will solve all of them. Correct? But the expression now will look a little bit more complicated. Do you agree?
Sir.
Yeah. Now, instead of 3, now if I have cubic, now I have to put 4. Even more complicated. Correct? So it gets more and more complicated as you add more and more variables and analytical becomes a little bit of a mess. Okay. In any case, there is another issue also. So let us say we took all these 6 points. You would have already seen this. You fit the line. Now, all of a sudden, a new person has another measurement and that person puts the measurement here. Now the line will shift. How will we find out how the line shifts?
We have to start from beginning.
You have to start from beginning. There is no easy way. If I add just one more point, n becomes n plus 1. Xi square becomes something else. Xi the whole square becomes something else. The whole expression has to be recalculated. But all of us intuitively know that the line should be close to this line. Do you agree? Okay.
Yes, sir.
So what we would like, so two problems. One is addition of features. By this, I mean, if I want a slightly more complicated model compared to the one that I had, requires completely new derivation. If you are doing an analytical method. Second, new data cannot be easily incorporated. So it is for these two that we use an iterative approach. Which is the general class of descent methods. In fact, Liebenberg-Marquardt also falls within this in one sense. Okay. So I hope everybody understood why we are not sticking to the old approach that we had, and we are going to try something new, gradient descent. So remember, we have these different types of regression. We have the simple linear regression, especially in one variable and analytical solution works well. You have non-linear regression. You have seen a little bit, even though you might not have used for non-linear cases. Well, you did. So you would have done Gauss-Newton and Liebenberg-Marquardt. In general, for neural networks, it's a generalized form of the above two, and we are going to use something that is called gradient descent. Now, technically speaking, you can use something like Liebenberg-Marquardt also, but Liebenberg-Marquardt, as you would have derived it, looks fairly complicated, and if you have a full neural network, it's kind of hard to do it, though for a single hidden layer, MATLAB does incorporate Liebenberg-Marquardt, and it runs blazingly fast on MATLAB. They have done some magic inside, and I am unable to see their code. They have done it really, really well. Okay, so let's now come to gradient descent methods. So all this was just to tell you the context. The context of a descent method is it's an alternative way of finding out the optimal parameters, and it's supposed to have two things. One, in case you add more data, you should be easily able to adjust the method so that you can add more data, and this is why gradient descent is very, very popular even in things like Google's face recognition, etc. Because the moment you give new data, it should basically be able to, and even spam filters, etc. So the idea is to quickly adjust whatever they have done before. Okay. Second thing is, it looks the same regardless of how many features you add. There are just some small changes. Derivation will not be very difficult. Okay. So the idea is any parameter finding problem, such as finding out the parameters of the linear model or the quadratic model or a neural network model, can be finally turned into an optimization problem which says minimize the difference between my fit and the original data. Okay. Now, what descent methods do is they use gradient information. In some sense, you have already used it. There are a whole set of common methods. There is gradient descent, which is what we will be doing, the extent of what we'll be doing in this course. There is something called Cauchy's steepest descent. That's really kind of hard to apply, especially with neural networks. There is conjugate gradient, and those of you who have taken my optimization course or Professor Balaji's optimization course would have seen these other methods. There are things called Newton and quasi-Newton methods, and Liebenberg-Marquardt is effectively something like a quasi-Newton method. Okay, all of these methods can be written in a very simple form. Okay, which is like this: the new iteration or the new value of the weight, I'll write it in W terms, Wi plus 1, I plus 1 instead of this, just one second. Just for clarity here, I'll write it in a different form. Wi plus 1 means I plus 1th iteration is the ith iteration plus, let's call this delta Wi. Remember, all W's are vectors. Why are they vectors? Because W, even in the linear regression case, has W0, W1, okay? And if you have quadratic, it can be W0, W1 up till Wn. Now, being a vector, it has two things. It has a magnitude and it has a direction. Okay? So you say that it has some scalar multiplying the actual direction. Okay, so the direction is S. So these are called descent methods, or so these descent methods work in a particular way. If you are somewhere in an n-dimensional space, you are at the location I, you want to go to the location I plus 1 in the direction S, okay, multiplied by a magnitude lambda. Okay. Now, what gradient descent does and what all general descent methods do is SI. Okay, this SI that I am talking about usually involves the gradient. I have written recall. This is from college. If you don't remember, that's still fine. Let me show you something actually. Just 1 second. Yeah, I hope this is visible. Yeah, people are still coming in, so I just need to admit them. Yeah, so let's look at this. This is a plot, okay, of the function x square plus y square. Imagine this is like a cost function which is w0 square plus w1 square, okay, something of that sort. So x and y, please do not confuse them with inputs and outputs. Just for convenience, especially this plotting routine uses x and y. But see this as follows: x and y are the parameters that we are trying to optimize against, and z is the actual cost. So for example, in the case of the slab problem, you had something like y minus y1 square and y hat square, which will look like w0 square plus w1 square, etc., etc. So let us say the function is w0 square plus w1 square, and that is the function I am trying to minimize, and we know that the minimum lies at 0, 0, and you can see this graphically. Okay. Now we are trying to minimize this function. So what is the question? I am going to make an arbitrary guess. So this is the three-dimensional view of the function. But typically, we are in the parameter space, which means if I rotate it, sorry. Yeah. So let's see it this way. So this is one parameter, this is another parameter. Let's say I make some arbitrary guess here, saying this is where the minimum is. Now from here, I need to get here. Okay. From this point to the final point 0, 0, I somehow need to get, and the iterative method would be somehow I need to move in an optimal direction at each point. So what gradient descent says, and the idea of gradient descent is that I will move always in the direction where the function decreases the most rapidly in a local sense. Let me explain what I mean by that. So you see these colors, these are effectively contours. What is a contour? Along the contour, the function is always a constant. Okay. Let's see the 3D function. Okay. What it means in the three-dimensional sense is that along the contour, I will always be at the same height. Okay. So if I am at the same height, imagine this is made of or this 3D thing is made of a bunch of springs, and we collapse all that and we see this contour plot. Okay. So we see this contour plot. Each of these lines, this yellow line, for example, represents a certain function value. This blue line represents another function value. Now, since each of these lines represents a function value, I know that if I move along the tangent, the decrease in the function value is going to be the least. Okay, least in the sense it's going to be 0. There is going to be no change if I move in this direction. And you might recall from your first year calculus that if I move normal to the contour, then my function will change the most rapidly. Okay, so that is if I start at this point, if I move normal into this direction, somehow locally at least I will change very, very rapidly. Okay, it might not work out globally. In this function, it happens to work out globally too. But in general, it will not necessarily work out. Let's just check another function. Okay, now you see that the contours are not circles. Okay, so they are something else. In this case, if I put a quadratic function, the contours will always be ellipses. Okay. So you can see that the contours, if you can somehow move perpendicular to the contours, this I am just saying sort of in a hand waving sense, I'll just prove it very quickly. You will always move in the direction of maximum descent locally. And that is the basic idea of the gradient descent method. Okay. So the basic claim is that the direction of the maximum change for any function. So if I take this function and I just showed you, this is the same function. These are the contours of that function sort of collapsed onto each other. So let us say the value of the function is 1 here, value of the function is 1.2 here, value of the function is 1.4 here. If I move along the tangent, the change is 0. If I move perpendicular to the contour, the change is maximum, which I am going to show. And the direction of the perpendicular to the contour is actually given by gradient of f. Okay. So when you want the change of any function f, okay, so let's say f is made up of f1 I cap plus f2 j cap plus f3 k cap. And we are moving in a particular direction v. V is itself v1 I cap plus v2 j cap. Sorry, I made a mistake with f. Please do not get confused. Oops. Sorry about that. F is a scalar, it's v, I should have written this way. F is a function, okay, of these two variables, v1 and v2, just like we just saw. Then del f del v vector. Okay, this is the gradient. So the rate of change along any particular direction is given by gradient of f dotted by that direction. Let me explain this. Usually I should spend a little bit more than what I mean by that is, in case I want the rate of change of a function f in the x direction, I will simply say that is given by del f del x. If I want this in the y direction, I will say it is del f del y. So the change in any general direction is del f del x I cap plus del f del y j cap dotted with whatever vector I want this change in. Okay. So del f grad f dotted with v vector. So let's say grad f is represented as g, then the rate of change of this function f with respect to a vector v in any direction vector v is given by mod of g, which is absolute value of grad f, or sorry, magnitude of grad f multiplied by magnitude of v multiplied by cos theta, where cos theta is the angle between grad f and this v direction. Now this means that this will be maximum when theta is 0 and minimum when theta is pi. That is, you will ascend fastest if you move along the gradient, and you will descend fastest if you move opposite to the gradient. Okay. So this is a very simple idea. The idea is this: at any point I look at the gradient, which will actually graphically it will point along the contour, or sorry, perpendicular to the contour, flip that direction and move in that direction. So therefore, when I want to optimize, I will say xi plus 1 is xi minus some constant. This is a scalar. I just know the direction. The direction has to be, it's a greater than 0 scalar. And the direction has to be minus grad f. So xi plus 1 is xi minus alpha times grad f. Very simple idea. Okay. So the idea is this: start with some random initial guess for the parameters, decide on some positive alpha. Let's call this the learning rate. Okay. In machine learning literature. This is called the learning rate. Presumably, if you have high alpha, you're going to learn fast. If you have low alpha, you're going to learn slow. So why not create very high alpha? If you create very high alpha, it will cause divergence. Very low alpha will cause very slow convergence. Then update your weights, and then you keep on iterating. Okay. Now notice that just in case we reach a local minimum, what would that mean? Remember, whenever you have local minimum, use this to derive. Let me use consistent notation. Call this grad f. So whenever you have local minima, in fact, that's how we found out our A and B, which was to set grad J equal to 0 or grad F equal to 0 or grad S equal to 0 at the local minima. It will automatically stop. As soon as it reaches minimum, it will stop. Okay. So the idea is simple. Xi plus 1 is Xi plus lambda star Si. Si is minus grad F and lambda star is alpha, a positive constant, which is called the learning rate. Okay. How do we stop? Again, you would have seen this previously, even with Leeuwenberg, Marquardt, etc. You should stop ideally when grad J is 0. It will never happen in practice because the number of iterations required could be effectively infinite. I'll show you an example shortly. Okay. Also, because your machine will do calculations only till a certain number of digits. So if you have a calculator, 8 digits. If you have, well, an 8-digit calculator means 8 digit. Usual computer will have 16 digits. Okay. So usually we will decide on some precision. We'll call it epsilon. I'll call it epsilon. Let's say we'll say I want 5 digits of precision. So you can have multiple options. You look at the previous iterations parameters and this iteration's parameters. Find out sum of their square. This means a norm. If you don't know what a norm is, it doesn't matter. All I am saying is just take the sum of all components. So if you have W1 k plus 1 minus W1 k square plus W2 is the second component, k plus 1 minus W2 k square, or in your old notation, AK plus 1 minus AK square plus BK plus 1 minus BK square. We need one number. So we'll say my parameters are now this, previously they were this. The difference between them squared and added should be less than epsilon. Another way is to find out all the components of the gradient of J, which we are just calculating, and ensure that they are smaller than an epsilon. Okay. Then you could also look at one particular, this is usually done in machine learning. Okay. Find out the cost function, how it is decreasing. Okay. So cost function meaning the actual final least square number that you are looking at. Okay. So which we call S, which you called S. So you could plot S versus number of iterations and see that after some time S will stop decreasing because this is the minimum possible that you can get. Okay. If it stagnates, then we can stop. So these are multiple possible stopping criteria. It will be easier for you to see when you actually do some examples. So the summary of the gradient descent procedure is decide on alpha and epsilon. How do we decide on alpha is a question I'll come to shortly. Okay. Make an initial guess, update the guess, and you calculate the stopping criteria. If you are satisfied, you stop. If not satisfied, you keep on going and calculate. So any questions at this point? Hello? Okay. Looks like there are no questions. So I'll just do a very simple example. And then tomorrow I'll do a slightly more complicated example. Okay, so I encourage all of you to participate. The same example. Let's say we want to minimize x1 square plus x2 square using gradient descent. we have an initial guess of 3, 4. You decide on an appropriate stopping criterion, and let's try experimenting with various learning rates. Okay. So initial guess, x1 equal to 3, x2 equal to 4. Let's call it x1 1, x2 1. Okay. The function I am minimizing, instead of f, let me call it j just for consistency. J is x1 square plus x2 square. At this initial moment, this is going to be 3 square plus 4 square. It's going to be 25. So let me set an alpha. Alpha equal to 1. Let us say. Okay. So what is the gradient? We first need to calculate the gradient. Del J del W1. What is this equal to analytically? Oh, x1. Sorry, I've been using x1. Analytically, obviously 2x1 del J del x2 2x2. Okay. So del J del x1 at this first iteration is equal to 6. Del J del x2 equal to 8. So this one is going to be x1 1 minus alpha del J del x1. This is going to be minus 3, and x2 2 equal to x2 1 minus alpha times del J del x2 going to be minus 4. Okay. Can you all do the next iteration and tell me what comes? So this is at the end of one iteration. This still gives us j equal to 25. Okay. So we can make a quick table. This is the iteration number x1, x2, and let's make j.
Oscillates between 3, 4 and minus 3, minus 4. Sir.
Correct. So the first iteration was 3, 4. This was 25. Second iteration we just saw is minus 3, minus 4. Now if you put minus 3, minus 4, you will get minus 6 and minus 8 as del J del x1 and del J del x2. Put that back. Okay. So you will get minus 3 minus 2 times minus 3. So you will get plus 3. Minus 4 minus 2 times minus 4. You will get plus 4. So at third iteration, you will get 3, 4 again. Okay. So what we see is when you choose alpha equal to 1, it does not converge. It in fact oscillates. Now if you choose, typically if you have some such behavior, if it is oscillating and if you increase alpha to 2, alpha equal to 2, okay, what will happen now? Can you try out?
Goes to very, very bigger values, bigger negative and bigger positive in consecutive steps.
Correct. So if you put alpha equal to 2, what will happen is, well, we can quickly check here. Okay. Del j del x1 is 6. If I put minus 2 here, what will come? 3 minus 12.
-9 -12.
Minus 9 minus 12. If you put that next, you will get 27 and 36. Am I right? So it will keep on going bigger and smaller or something of that sort, somewhere close to that. So you will go to very large values. This will diverge. Okay. Alpha equal to 0.5. What happens? Can everybody try?
It at once come to 0 and stops there.
If you put alpha equal to 0.5, you will get x12 is 0, x22 is 0, and then x13 is also 0, x23 is also 0. Why is that? Because the moment I hit 0, 0, my del j del x1 will be 0, del j del x2 will also be 0. So it will not update. Okay, so it has converged in one step. Okay. Now, if you take alpha equal to 0.1, x12 will be 3 minus 0.1 times 6, 2.4. 4 minus 0.1 times 8, 3.2. Okay, so if you try this, you will see that this will converge slowly. Oops. Okay, the point is this: depending on what alpha is, it can either oscillate or diverge or converge very quickly or converge very slowly. So all these sorts of behaviors are possible depending on what alpha you choose. So alpha in the machine learning or the neural network literature is called a hyperparameter. Okay, I will talk about this again tomorrow. So it's called a hyperparameter, which you also have to specify for the problem. Okay, and typically there is no easy way of doing it. A lot of trial and error goes into this, and there are other protocols in order to find it out iteratively, in order to change it during a convergence, during a optimization process, etc. So I am not going to get into that. So for now, we will assume that somehow or the other we have found out this alpha, maybe by trial and error. Let's assume that's how we are doing it, and we will use that in order to solve our gradient descent problem. I would like to show you one final thing here, and then I'll end for today. So is everybody able to see my MATLAB screen?
Yes,
Yes, sir.
Okay, so here I have programmed this gradient descent thing. So let's make this 0.1. Okay, what I have done here is, so here you can see my function. I have written my function here, x1 square plus x2 square. These two are the gradients, df1 and df2 are the gradients, 2x1, 2x2. Okay, this is some plotting routine. And here is my initial guess, 3, 4, okay, just like what we had. my epsilon is 10 to the power minus 5. Okay, so I have chosen an epsilon of 10 to the power minus 5. And the way I am determining my epsilon is, so the convergence criteria is the current step minus the previous step, the difference in the parameters. Okay, so that's how I am doing it. Okay, so if I run it, so you can see that it took 53 iterations. Okay, so it took 53 iterations. The first iteration was exactly the same as what we calculated by hand, 2.4, sorry, 2.4, 3.2. Okay, so we started there. After 53 iterations, I have come to 10 to the power minus 5. We will just play with alpha values a little bit just to show you. Yeah. Now notice this, these are my contours. Okay, so I started here at this point, 3, 4. You can see that. The next point after that iteration was 2.4, 3.2. Now notice something, and this is why I plotted it. You will notice that each point, if you see roughly, the direction in which it moves is perpendicular to this contour. That's because we are moving along the gradient. Now this is easy to visualize when you have just two parameters. Neural networks typically have millions, and the language models that YouTube uses for transliteration, etc., have close to a million, billion parameters. So there is this language model which has billion parameters. Luckily, when we do neural network problems, it is still 100, 150 parameters. Typically for engineering examples, simple engineering examples. But even that, you can't imagine the actual 100-dimensional space. Because we have two parameters, we are imagining in the 2-dimensional space, and I can show you nicely that it is moved. It is moving perpendicular to the contour or along the gradient, etc. In 100 dimensions, obviously, none of us are capable of imagining it. But this goes, and you can see finally it converges close to the final value. You can see x1 is some 10 power minus 5, x2 is 10 power minus 5. Okay, so it starts from the beginning, goes till the end, and this is how it converges. Of course, if I do something like alpha is 0.48, okay, if I take a very high alpha, you'll see it converges in 6 iterations. Okay. So that is the effect of having a very high alpha, a very big jump right at the beginning, and then it moves fairly quickly. But if we try to get greedy and try to increase alpha beyond that, it can start diverging. Okay. So this is what, let me actually experiment with this. What happens at alpha 0.55? I don't know. Yeah, it actually converges. So it depends on what alpha you use. If I use a divergent alpha, it will go back and forth as all of you saw. Or if I use alpha greater than 1, it will actually start diverging. Okay, so what we will do tomorrow is do another example using gradient descent. And if I get the time, I will start back propagation. Thank you. If
Sir,
you have any questions, you can ask. Sorry. Yeah.
sorry, sir. I have a doubt regarding the multiple options for stopping criteria.
Sorry. Yeah.
So in one of the slides, you wrote J of in the last point you wrote J of W of k plus 1 layer, k plus 1 iteration minus J of W of k plus 1.
Oh, is that what I wrote? Sorry,
Yes, sir.
should be K. Okay.
Yes, sir.
Thanks for pointing it out.
Sure, sir.
Anything else? Other questions? Okay. If not, thank you.